Hello everyone, my name is Briana Dandridge. I am currently a freshman at Norfolk State University where I'm majoring in optical engineering. Now, because I'm an engineering major, it is mandatory that I take a course called Introduction to Engineering. With that being said, every semester, we are given a project. So this year, my semester in this class, we were given a project to do to design, build, and test a solar powered water heater that could bring no less than 1 liter of water to boiling temperature. So I did it with two other people, and they're coming out here right now, but you're gonna hear from me right now. Okay, so I want to start with our priorities and our objectives for my specific group. Now, for us, we really wanted it to heat fast because this is something that's supposed to be, how do I say, marketable. And if it doesn't heat fast or if it takes too long to heat, nobody's going to want it. It's going to be pointless because there's a whole bunch of other things that they can use other than this to heat up their water faster. Another thing is we want it to work. So not only fast heating is a part of it working, but we need it to work. At least, heat up something. It might not bring it to boiling temperature, but we want it to work or get it to the point where we can see how far we are. And if it is working, then that's great. And if it's not working, at least we can move on from there. Not something where it's just not working and it's just pointless. We also want it to be affordable because I didn't mention this before, but this isn't a solar water heater that is going to be already built and put on the market. It's something that we want you guys to do yourself, something that you guys might be interested in, building yourself. We also want it to be portable, so that way it's easier to carry around and definitely better for transportation. And last but not least, we want a rugged construction, which means we want it to be sturdy. We want it to be strong. So whatever happens to it outside does not affect it, so it does stay intact. Now, for our target audience, we made this very, very specific because it is a do-it-yourself project. Now, for our target audience, we want 29 to 56-year-old males and females who, undertake at least one project every 3 months. Do a lot of repairs or upgrades to their homes, and spend, around between $250 to around $3,000 in home stores like Home Depot and Lowe's. Now, our inspiration came from a device called a solar water cooker. It's a parabola shaped with a tube in the middle, and it is lightweight. It only weighs 2 pounds. It's compact, it's portable, and it heats up water really fast. It's very convenient for skiing, camping, fishing, going to the beach, etc. So that was really where our inspiration came from, especially because it brings it to boiling temperature, and that's the whole purpose of our project. Now, for our first attempt, we did not do that well. We basically made a device that was square shaped, and there was no way that light could hit the reflecting surface onto the water source of what our water was being in to be heated in. It was a box. It was straight. So the light would just hit it, but it would not be reflecting back, which means it was just straight. We needed like a parabola shape so that it would hit it and all the energy would be absorbed by the water. For our final project, I have some pictures. It looks like this. Oh, sorry. Okay, well, that's enough. So basically that's what we did for our final project. Because it is a do-it-yourself, I will be posting the instructions and also the materials needed down below. And the total cost for everything you would need, and this is including stuff that you might already have, is around $220. It's not bad, especially for a do-it-yourself solar water cooker. Now, for our specific water heater, we have some specific features in our design that we wanted to point out because they're very important. So first, we would like to point out our handles. Now, our handles, remember earlier I said we wanted it to be better for transportation. We wanted it to be portable. So with having those handles, it makes it so much easier because it is very heavy. It makes it easier to carry from one destination point to another. So also we have adjustable reflecting surfaces. So with that, let me show you. In the corner right here, this whole piece right here is a flat. And with the purple string, you can tie it around a bolt to move it in, move it out, basically wherever it needs to be so that the light is shining back onto the pipe. So we have that on both sides. And we also have an adjustable pipe. So one side of it, the pipe is soldered onto a piece that is connected inside by a hole, and on the other side we have a string connected to our piece that is connecting the two tubes together. And that's basically for, you can lift it up when you're pouring the water out, when you're draining the water out of the system, or when you're putting water into the system, you can make the base lower. Also, we have a parabolic shape. And that's what I was talking about when we did our first attempt. It wasn't so much of the lights wasn't hitting our box in the right direction because it was straight up. We needed to be at an angle so when it hits, it goes to the light source. Go from the light source goes to the water source. Okay. So I want to touch on radiation, conduction, and convection. So all of our collection is heat due to radiant energy from the sun. Having our pipe painted black to help collect more radiant heat. Because our pipe was exposed to air, it was susceptible to convection loss, and that's a negative. Also, because there was no insulation, it was also susceptible to radiant heat loss. The reflectiveness of our panels was a positive because it helped keep radiant heat within our system. Because we used copper piping, our conduction of water was very high because copper, when painted black, heats up very well. But another thing, the problem with using copper, it cools down just as fast as it heats up. So we had to be really careful with that. Now, so for our overall efficiency, I have some calculations I want to share with you. So our initial source, which was the sun, gave us, when we tested, about 275 watts per meter squared. Now, for the area of our system, because it's a square, the dimensions are the same. So it was 2 feet by 2 feet. So that gives us 4 feet squared for our area. Now, to convert this, we had to convert this to meters squared, from feet squared to meters squared. 1 square foot is 0.0929 square meters. So that means 4 feet squared is equal to 0.37191216 meters squared, or in other words, our area was 0.37 meters squared. Now, to find our captured wattage, we had to multiply our area times our initial source. Now, our area was 0.37 and our initial source was 275. So when we multiply those together, we get 101.75 watts. Now, we tested our system for 1 hour. So 1 hour converted in seconds is 3,600 seconds. Now, to find the amount of energy received by the system in joules, we had to multiply the captured wattage times the time in seconds. And our captured wattage was 101.75 watts times 3,600 seconds, and that gave us 366,300 joules. Now, we had to convert that to kilojoules. So 1 joule is equal to 1,000 kilojoules, so we had to divide that by 1,000, and we got 366.3 kilojoules. Now, to find the amount of energy absorbed by water, we use the equation Q equals Cm delta T. Now, I'm going to define each of these for you. C is equal to specific heat of water, which is equal to 4.187. Mass, which was the mass in grams. We had to measure in grams to use this equation. Now, to convert liters to grams, we had to do a couple conversions. First, we had to convert. We used a half a liter of water for our measurements. We had to convert half a liter to milliliters, which gives us 500 milliliters. And then we had to convert milliliters to grams. Now, 1 milliliter is equal to 1 gram, so the conversion was not that hard. So it just went from 500 milliliters to 500 grams. So that was our mass. Our mass is 500 grams. Our delta T is our change in temperature from when we start to when we finish. So our beginning temperature was 20.75 degrees Celsius. Our ending temperature was 38.2 degrees Celsius. The difference between those is 17.45 degrees Celsius. So that's our delta T. Now when we use the equation and put everything together, we get 4.187, which is the 4.187, which is the specific heat of water, times 500 grams, times 17.45 degrees Celsius, which is our delta T. And we get a total of 36.531575 kilojoules. Or in other words, Q equals 37 kilojoules. Now, to find the overall efficiency of our device, we had to divide the amount of energy absorbed by the water by the amount of energy received by the system, all multiplied times 100. So that's 37 kilojoules divided by 366.3 kilojoules, which gave us 0.1010 times 100 gave us 10% for our overall efficiency. Now, our performance results were not that high. They could have been better. We did take some time to actually do the project and actually get it done. There's no excuse for that. We should have jumped on it. We should have done better with timing. And I feel as though if we would have got it done in time or got started on it a little bit quicker, we would have had more time to finish it, more time to test it, more time to make adjustments so that we could have had the best project it could have been. So one thing I do want to comment on is our next generation improvements. So we want to include a Fresnel lens on the top of our box. Fresnel lenses, they focus the sunlight onto one point. So if we use a Fresnel lens, we can focus all of our sunlight onto our pipes, which will heat our pipes tremendously, will really help with heating our pipes. Also, we need a water source because when we were trying to put the water inside the tubes, because they are flat, we had to lean the system over to put the water inside. Even though the adjustable pipe we made the pipe adjustable for that reason, it still wasn't exactly where we needed to be. Now, if we use a water source, we'll have the energy to push the water through so that both pipes fill up and we'll have more accurate results. Oh, another thing is, when we use a Fresnel lens, we're going to be closing off the top of our box, which helps also tremendously with conductivity. So I just want to say thank you for watching this. I hope you enjoyed it. That is my project for Introduction to Engineering.